oxygen is the same, so on and so forth. So there's a lot of similarity, and of course some differences as well. Is water polar?
Yes.
Right?
Yes.
For us, that's as polar as things get for organic chemists. So should we expect alcohols to be polar?
Yes.
In the same direction as water is, except there is one difference between the two, that alcohols have an R group. So the overall polarity of the alcohol depends upon how big that is. Remember last quarter, first lab, when we discussed solubility as a function of polarity, and we talked about organic molecules being a combination of a polar group and a non-polar portion. Whichever portion is bigger takes over, the molecule takes over that characteristic. So definitely, this is a polar bond, no doubt about that, which is capable of doing hydrogen bonding and all, but this is non-polar. So as the non-polar part becomes bigger and bigger and bigger, the overall polarity goes down. Exactly. Which we can see in their solubilities, and we can see that in their boiling points and all of that stuff. We can see that influence, that as R gets bigger, the overall polarity of alcohol goes down. Make sense, everybody? And I don't know if you remember, one of the parts in the lab was actually exploring that. I think you guys explored the solubility of methyl alcohol, butanol, 1-butanol, and was it octanol? 1, 2,
Yeah,
3,
octanol.
4, 5, 6, 7. 3, 4, 5, 6, 7, 8. We explored their solubility in water and hexane, I think. Right? So hopefully you saw that trend, that which of these do you expect to be most polar?
Methanol.
And right, do you guys agree?
Yep.
That the polarity we expect to go in that direction, because even though they all have a polar piece, but the non-polar portion is different. So as the non-polar portion becomes bigger, the polarity goes down. So which solvent do you expect methanol to be more soluble in, water or hexane?
Water.
Absolutely, I hope that's what we saw last quarter. And what about octanol?
Hexane.
It should not be soluble at all in water. And carbon 4 is kind of the threshold. For every one OH, C4 is where we are now making a transition from being polar enough to being non-polar enough. So maybe you saw some solubility, partial solubility here, or maybe you didn't, it depends upon, but definitely in hexane. So you'll see those trends in the different physical characteristics of these compounds. Does that make sense, everybody? Yeah? Okay, what about water? Do we consider water to be a strong acid?
No,
So
it's
then why should an alcohol be a strong acid? It's not. pKa of water is about 15. This, generally speaking, alcohols, pKa's are 15 through 16, somewhere in that range. Not very strong acids. Unless you have a strong base, these don't want to give a proton. What about base? Do you expect water to be a strong base? Is water a strong base? No. So then why should we expect alcohols to be a strong base?
They
No,
can't be.
They aren't. Alcohols, just like water, are weak acids and weak bases. From Gen Chem, does a weak acid react with a strong base or a weak base?
Strong base.
Does a weak base react with a strong acid or a weak acid?
Strong acid.
That's a very important thing to keep in mind. Weak combination doesn't work. Either strong combination works well, or strong weak combination works as well, but weak combination does not work. So just like water, alcohol is a weak acid and also a weak base. So unless the other thing is a strong whatever, they will not do anything. Make sense, everybody? Yes? So is this possible?
No.
Not at all possible. That's a weak base. I mean, it's acting as a base, right? It's taking a proton. So, but is it a strong base or a weak base?
A weak base.
And this is acting as an acid. Is it a strong acid or a weak acid?
Weak
So
acid.
should the equilibrium be in the direction of the stronger acid, or is the equilibrium in the direction of the weaker acid?
Weaker acid.
Absolutely. The equilibrium will be in that direction. Water can't do it. Unless you're reacting these guys with a strong base, then they will act as an acid. Or if you react them with the strong base, acid, then they will react as a base. But on their own, they won't. Does that make sense? So the point I'm trying to make here is whatever you expect for water, expect the same for alcohols because the structures are similar. The only difference is the R group. So if the R gets bigger, the molecule becomes less polar, and so on and so forth. Are we okay, everybody?
Mm-hmm.
Cool. So then to draw another parallel between water and alcohols, have you watched those videos on YouTube? Because there are quite a few scary ones where people are dropping chunks of sodium in the lakes, and what do you see happen? Boom.
What? I've never seen that.
Why? Check it out. People are crazy sometimes. Or maybe all the time. Why? What's that boom for? What does sodium do? And it doesn't have to be sodium, it can be lithium as well, potassium to some extent. What does sodium do when you put it in water? Why is there such a big boom?
Because the sodium reacts with the
To make what?
sodium
Absolutely.
hydroxide.
Exactly, and
H.
H plus can't exist. H2.
H2.
Can I write this as sodium hydroxide like that, just to show that one of the hydrogens is taken as a proton? Of course it's taken as a proton, but then there is a redox reaction that happens which creates hydrogen gas.
yeah.
And this is a highly exothermic reaction, hence the big boom. When I was in grad school, again, that was a long time ago. It's funny how when I used to tell this story when I started at Everett, it didn't feel like it was so long ago. Now I'm like, that was 40 years ago. Anyways, coming back though, when I was in grad school, UT Austin had a big accident in the chemistry department. So we used to, in the graduate lab, one of the ways for us to clean our glass, where we used to have these buckets of sodium, highly concentrated lye solutions, and that would have chunks of sodium in it. And I think in UT Austin, a grad student by mistake, somehow pieces of sodium went into their water system. It went down this drain in the water system, and what happened? Boom. They had a pretty big fire in the chemistry department. Why? Because sodium came in contact with water. A lot of heat created, a lot of energy created, right?
Mm-hmm.
So if water can do that, why can alcohols not do the same thing?
Because it's missing the
The answer is yes, they do exactly
they
the
do?
same thing.
Mm-hmm.
There's a polar OH bond, there's a polar OH bond. Can someone tell me what will be the outcome?
Sodium
There's
hydroxide.
no sodium hydroxide this time. That's why I drew it out that way so we can see the parallel.
The NaOR.
Exactly.
NaOR plus H plus.
H2. The point is, if you compare the alcohol to the sodium alkoxide, do you all recognize that this is ionic?
Yep.
This ion from an alcohol, this ion is called alkoxide. What have we done basically? From alcohol to alkoxide, what has happened? What have we removed? Or what have change has happened?
We took out
Proton.
we took out a proton.
So what did this act as? If it gave a proton, what did this behave as?
An acid.
Exactly. So if we want to deprotonate an alcohol, which is a weak acid, we need something that is a much stronger base to do so. So one of the ways in which an alcohol can be deprotonated is by using sodium. Just sodium metal. Lithium metal also does the same job because lithium is also a very active alkali metal, can do this very easily as well. The point is, if I needed to deprotonate an alcohol which is a weak acid, an ordinary base won't work. We need something like sodium or lithium. Or, have you seen another very strong base so far? I wouldn't ask if the answer weren't yes. Which one? Amine.
Sodium
Very
amine.
strong base. Another very strong base that can be used in this deprotonation of an alcohol which is a weak acid is sodium hydride. A very strong base because their conjugate acids are very weak acids. So they are very strong bases. So the point I'm trying to make is that if I needed to deprotonate an alcohol, can I just do sodium hydroxide? Will that work?
No.
Nope, it won't work. How about I use sodium methoxide? Because we've seen those act as bases also. Will that work? Nope, not strong enough at all. We gotta use a base that is way stronger. And the only way to deprotonate an alcohol, just like to deprotonate water, is to use either a sodium metal or lithium or sodium hydride or sodium amide. These are the strong bases. Otherwise, you can't deprotonate. Can someone tell me what's the conjugate base of this alcohol?
It's alkoxide.
So this is 1, 2, 3, 4 butanol, so butoxide. Of course, sodium is the counter ion. Everybody okay?
Mm-hmm.
Now, is this alcohol, is this a strong base or a weak base?
A weak base.
So if it's a weak base, it is also a weak
Acid.
No, not really. Nucleophile.
Weak nucleophile.
What do bases do? By the way, this is something I read in your answer to the last question for the exam retake also. Do bases do eliminations or substitute? Okay, now let's start with nucleophile. What do nucleophiles do?
Substitution.
Not elimination. So if you're talking about elimination, please don't call it a nucleophile. Nucleophile doesn't do elimination. Nucleophile does substitution. Who does elimination? So, would alcohol be a good base to use for elimination? If I wanted to do elimination, do you think that would be a good choice to make? It's a weak base.
Yes.
So do you think that's a good choice?
Yes.
Not at all.
No,
Okay, why? Oh, calm down. To have an elimination happen, and when I'm saying elimination, I mean E2 because E1, unless for alcohol, but alcohol E1 doesn't use a base. Alcohol E1 uses what do we need to dehydrate an alcohol? An acid. It doesn't use a base. That's totally different. If you think about bases, if I wanted to do elimination, do I need a strong base or a weak base?
Strong.
So do you think this is a good reagent to use to do elimination?
No.
No. How about substitution? If I wanted to do substitution, do I need a good nucleophile or a bad nucleophile?
Good.
So do you think an alcohol is going to be good for SN2?
No.
Maybe for SN1, because SN1 uses weak nucleophiles, it's okay, but for SN2, it's not going to be a good choice to make. Isn't that right?
Mm-hmm.
But then what about the conjugate base of the alcohol? What about this guy? Is it a good base?
Mm-hmm.
It's a decent base, absolutely, it's a good base. Of course, it's not as strong as these guys, those are very strong bases, but it is definitely a good base. And is it a good nucleophile?
Yeah.
Absolutely. What do bases do? What
Okay.
reactions do bases do? Elimination, E2, specifically E2, right? What do nucleophiles, good nucleophiles like to do? SN2. So, can I use this guy and react it with what will that create? After I've deprotonated the alcohol, I've removed the proton from an alcohol, and then I take that alkoxide, reacted with that, what do you expect to happen? So, as a substitution or elimination? Why? Because that's primary. So, of course, there's SN2 plus E2, but SN2 will be the major pathway because that's primary. So, absolutely, what did you say? Exactly. You'll make an ether. Do you all understand this? Everybody gets that? Sure? Okay, we'll come back to this reaction a bit later in this chapter. We'll come back to look at this reaction more a bit later. Right now, what I wanted you to understand is alcohols are weak acids and they are weak bases. So if you wanted to deprotonate an alcohol, we have to choose something that's a strong base. Sodium, lithium, sodium hydride, sodium amide, those are good bases to use to deprotonate an alcohol. Are we okay, everybody?
Mm-hmm.
Yes? Okay. Synthesis of alcohols. Most of this, some of these we've already seen, a couple of them are new. So let's look it up. What family of compounds can we make an alcohol from?
Alkene.
Alkenes, okay. What is that reaction called? Hydration. What are we using? Acid. Are we adding acid to across? How about call it an aqueous acid or dilute acid? Why? Because we need water. You're adding water. What's the role of the acid? What is the role the acid is playing there? It's a catalyst.
Mm-hmm.
Of course, yes, it's going to protonate and then you're going to recreate it. If you write the mechanism, we've written that mechanism a number of times. But yes, the role of the acid is a catalyst. The actual reagent is water. Can I write the same thing as plus H2O? Is there any difference between the two? None.
No.
They're all saying the same thing. Because what is H2O and H plus together?
H3O plus.
So there are different ways people write it, but it means the same thing. Are you guys with me? Yes?
Mm-hmm.
And yes, absolutely, the product is an alcohol. We have written this mechanism. You have to know this mechanism, be able to write it no matter what. We've talked about the intermediate carbocation, rearrangement, Zaitsev's, no, not Zaitsev, excuse me.
Markovnikov's.
And blah, blah. We've talked about all of that. Is everybody okay with this?
Mm-hmm.
Okay. What else can we make an alcohol from?
Alkanes?
It's right here. We just did that.
Oh.
What else can we make alcohols from? This is Marx. Oh, two other ways of making it. Sorry, I totally. So what is the second way of making it?
You got HG.
Oh, is that what you meant, Carter? When you said? I think so. Yes, and what does that sodium borohydride? What kind of alcohol does that give us? Marx, okay.
Without rearrangement.
Without rearrangement, okay. And we did not have to write a mechanism for that. Without carbocation, so no rearrangement. Is there another way to do so? Convert an alkene into an alcohol?
The other one was just anti-Marx.
Which, and what are we using?
BH3 or B2H6.
BH3 or B2H6. Choose one. And in a base in sodium hydroxide. And this gives us the anti-Marx without rearrangement also because there is no carbocation. We did not write its mechanism either. The only mechanism that we need to be able to write is this one. Isn't that right? Mm-hmm. Everybody? Okay, cool. What else can we make an alcohol from? Something that we spent like 5 weeks on at the start of this quarter, 4 weeks perhaps.
Alkyl.
An alkyl halide,
An
exactly.
alkyl halide.
If you have an alkyl halide, how do we convert that into an alcohol? What reaction are we talking about? Substitution. So what kind? Is it SN1, SN2? That depends on this guy.
Mm-hmm.
Isn't that right?
Yep.
Depends on this. So if this is primary, would we want SN2 or SN1?
SN2.
So if it's SN2, what should be our nucleophile? If I want to get OH on there, what should I use to carry out an SN2? Come on guys, we've done this quarter. Huh? RO minus. Oh, why RO minus? But that'll become ether, it'll become OR.
Oh.
HO minus.
Hydroxide.
Isn't that right? You're trying to replace X with
Yep.
OH. But if it is tertiary, do we want it, will it go through SN2 or SN1?
SN1.
So do we want a strong nucleophile or a weak
Weak.
nucleophile?
Weak nuclear.
What's a weak nucleophile
Water.
version of OH?
Water.
Water. Now what if it's secondary? Now that's tricky because secondaries can do both and they can also do eliminations pretty well. So that's going to be more of a temperature dependent phenomena. If we want to do SN2, of course, you got to go with hydroxide, but if you want to do SN1, you got to go with a weak nucleophile. Do you guys remember all of this? Yes? So these two reactions we've already seen of how an alkyl halide can be turned into an alcohol. Questions? The next couple of reactions are new for us. So to make an alcohol, so this is reaction 1, reaction 2. The next couple of reactions, 3 and 4, are new for us. So alcohols can also be created from compounds that have C double bond O. Can someone tell me which family of compounds have C double bond O's in them?
Ketones, aldehydes, carboxylic
Okay,
acid.
what else? Ketones, aldehydes, carboxylic acids, what else? Functional groups? Esters, what
Esters.
else? Ketones, aldehydes, carboxylic acids, esters, what else? The one that has who, what?
Acid anhydride.
I'm laughing on the outside, to be honest, Kerry, but my insides are like, anyways.
Acid anhydride.
Acid anhydride is the one with the 2. What else? Great! Huh? Amides and one more. Acid halides. Get our functional groups, guys. You gotta know our functional groups by now. So, some of these compounds can be converted into alcohols. The first method we will look at is through reduction reaction. Now, there are 2 reducing agents. Actually, you've seen them already. We are reintroducing ourselves to these 2 reducing agents. One of them is sodium borohydride. Do you remember this guy?
Mm-hmm.
Now, please notice sodium is just a counter ion. It's the borohydride, which is the actual reducing agent, which is the actual reagent. Can someone remind me, when did we learn about this? Which chapter, what part, what topic did we?
It was chapter 8 when we went over alkenes.
Alkyne.
What context?
Okay.
After adding the
Oh.
MCBPA.
So we reacted epoxides with these
Epoxide.
guys, right?
Mhm.
And what did they do? What were they supplying us with?
Protons.
No, they can't.
Hydrides.
Hydrides. Let's get our vocabulary. If something is electron rich, how can it give us H plus? Not possible. So, but yes, it's a good source of hydride. But without creating it, it just allows us to get one from there, right?
Mm-hmm.
Is there another version of this that we also saw at the same time? Sodium borohydride, there was one more that we saw which does exactly the same thing.
Yeah.
Aluminum hydride.
Lithium aluminum hydride.
Lithium aluminum hydride. Okay.
By the way, don't be surprised if sometimes people call this La. Lithium aluminum hydride.
Oh.
That's an abbreviated form of it. Again, the counter ion does nothing. The actual hydride source is the aluminum hydride part. We also said when we use them that sodium borohydride is weaker than lithium aluminum hydride. This is a very strong reagent. So much so that it cannot be exposed to moisture. We don't have it in our lab because we are not able to keep it safe. We're not able to store it in such a way that it doesn't come in contact with moisture in the air. So we can't have this in our lab, but we do have sodium borohydride because it's weaker. Make sense, everybody?
Mm-hmm.
So the point, why is that important? It is important because when we use sodium borohydride, it is okay to use it with a protic solvent such as methanol. Totally okay to do so, and we'll write mechanisms and also we'll understand why that is needed. Totally okay for them to coexist or be together because sodium borohydride is safer. But can't do it with La. Lithium aluminum hydride being such a strong reagent, there cannot be any protic solvent around. So therefore, this will always be step 1, and there will always be step 2 where you add a proton to whatever the mechanism is. But they have to be separate. They can't be together. So when I'm going to write reaction equations, when I'm using sodium borohydride, I can take this together with methanol, no problem. They're together. But if I'm using La, I cannot have La with the protic together. Not okay. That won't work because these two will react with each other instantly. So I have to make sure I do the La part first, finish it off, get whatever that creates, and then react whatever that creates with water. So they have to be separate. Do we all understand the difference between these two, the ways of writing? This is take them, throw it in one pot. This is no. Finish that first, and then whatever you get from there, you react it with that. Everybody okay? Okay. So, as I was saying, sodium borohydride is weaker, La is much, much stronger. So, there are some family of compounds, namely aldehydes and ketones. Let's start with these. They can react with both sodium borohydride or lithium aluminum hydride, either reagent. So they can either react with sodium borohydride in alcohol solvent or lithium aluminum hydride. Please notice the difference how I'm writing it. Sodium borohydride can be with the methyl alcohol, but lithium aluminum hydride has to be separated from protic solvent. They can be together. And the idea is that it undergoes a reduction reaction where hydrogen gets added across the pi bond. Hydrogen, one of them goes on the oxygen, the other one comes to the carbon and it becomes an alcohol. It's a reduction reaction because we are adding 2 H's. We are adding H2 across the pi bond. But it's not called hydrogenation because there's no H2 in this system, right? You don't have hydrogen gas in this system. So we don't call it hydrogenation, but you can definitely call it reduction. Everybody okay?
Mm-hmm.
So can someone tell me if we did this with a ketone, what would we get? Same thing, same idea. So you can either do sodium borohydride or La, one of those. But what does it create? And what? Agreed?
Mm-hmm.
Yes?
Alcohol.
Everyone okay? Can someone tell me what kind of an is it that came from an aldehyde? What kind of alcohol did we create by reducing an aldehyde?
Secondary.
Is it? Is that secondary?
Oh.
Do you all agree? Because it already had an H, we are adding another H here, an H there, so that becomes primary. Agreed?
Mhm.
How about the ketone? What kind of an alcohol, sorry?
Secondary, but I think you wrote primary one.
Ah, yeah, because
Yeah.
there we go. That's a mistake. Yeah, absolutely. Correct. Secondary. So when we reduce a aldehyde, we'll get a primary alcohol. If we reduce the ketone, we will get a secondary alcohol. Are you guys with me? Yeah? So let's see some specific example and mechanism. Write a mechanism, try and figure out how is that happening. And then we'll go to some other families of C double bond O compounds because they can also create alcohols using one of these. So, but let's just focus on aldehydes, ketones for now. By the way, when you look at this reaction that's on the board, did the number of carbon atoms change?
No.
That's very important thing to note. And why is that so important to note will become evident just a bit later today. But let's look at some examples and let's figure out how is this happening. So,
One, two, three, four.
can someone please tell me what will be the product
H.
in 2 seconds? That's a reducing agent. You have an aldehyde. What will that become?
And to
Agreed?
Huh.
Let's write a mechanism. Let's try and figure out how is this happening. So, C double bond O, is that polar or non-polar?
That's
Is the C double bond O polar or non-polar?
polar.
Why is it polar?
you have two bonds.
It has two bonds what?
It's going in the oxygen is more.
So is it just because of the electronegativity that bond is polar? That's inductive effect, isn't that right?
Mhm.
Oxygen is more electronegative than carbon. It is pulling the electron density. That's called inductive effect. But is that the only reason why this bond is polar?
Resonance.
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 Can you please draw the resonance structure of the aldehyde?
I have no idea.
Oh, come on. Ninth week. That's it.
Yep. Oh,
So what's the hybrid
Wrong.
of the two though?
wrong resonance structure.
What's the hybrid of the two? Isn't that right?
Yep.
So that bond is very polar, but not just because of the electronegativity difference, it's also that resonance thing that's going on,
Resonance.
which pulls the pi electrons towards oxygen. So the question is, because of that, what can we say about this carbon atom? Is it electron rich or electron poor? Electron poor. If it's electron poor, what can it react with? Nucleophile. Where's the nucleophile? So this is an electrophilic carbon. That carbon is electron poor, it's electrophilic. It needs to react with a nucleophile. Where is the nucleophile? That is what is being provided to us by the aluminum hydride. What is aluminum hydride a source of?
Hydrides.
H minus, exactly. So one of those hydrogens goes with the electrons and attacks that carbon. But then what happens to the pi bond? If that happens, what happens to the pi electrons? They go to the,
Oxygen.
what does that create? So the nucleophile attacks the electrophilic. There was already a hydrogen. Another hydrogen comes in here. Do you guys agree? Everybody okay?
Mm-hmm.
What is that? What is that? Without complicating things too much. It's an alkoxide ion.
It's an
isn't it?
alkoxide and
It's a conjugate base of an alcohol. What does this need to do to become an alcohol? Louder?
Deprotonated.
Deprotonate. You said
Protonated.
deprotonate or protonate?
B coordinated.
Be protonated. Is that what you said? Add a proton? Exactly.
Mhm.
Now, where is the proton coming from? That's why we need
H2O.
the protic solvent to bring a proton from. So, when the protic solvent, in this case water, now that's a stronger base, so therefore this can act as an acid. Gives us a, so if I were to color coordinate all my atoms, because I'm going to ask you a question where this might be useful information, where did this black hydrogen come from? Anybody?
The water.
The solvent, right? What if the solvent weren't water? But the point is that the protic solvent gives us the hydrogen on the oxygen. Isn't that right?
Mhm.
But where did the hydrogen, the red hydrogen on the carbon come from?
The aluminum
That
hydride.
came from the reducing agent. You guys with me, everybody?
Mhm.
Okay, so if that makes sense, let's try with the ketone and let's see what is that going to do. So please go ahead. This time I'm going to use sodium borohydride. This, please note, remember sodium borohydride can be in contact with protic solvent because it's a weak reagent. But the point is, what will be the product, and can we write a quick mechanism to explain that product? Anyone? What's the product?
Cyclopentanol.
Right? Basically, the ketone is becoming an alcohol, right? One of the H's went here and another went there. Let's write a mechanism. So, the double bond, the carbon of the carbon oxygen double bond, is that electron poor or electron rich? Right?
Electron poor.
So, it's electrophilic. So, a nucleophile can attack it. Isn't that right? What is the nucleophile that's coming from borohydride?
A
A
hydride.
hydride with the electrons attacks, which means the pi electrons shift. What does that create? Sorry, could you say that again?
An O minus.
O minus, exactly. And where did this hydrogen go? It went to the carbon, right? And
Yep.
what is the O minus going to do?
Get a proton from
And
water.
where is it going to get a proton from?
Solvent. C3OH.
So once again, please note, and that's the only reason I'm color coordinating it so you guys can see that the hydrogen on the carbon came from the reducing agent, whereas the hydrogen on the oxygen came from the solvent. You guys with me? Does the mechanism make sense? So if that does make sense, please let's try these. And here I'm not asking for the mechanism, I'm just asking, thank you so much, for the product. Does everybody understand the mechanism here?
Yes.
Okay, cool. What is D? Have we seen D before?
Deuterium.
Cool. What is deuterium? Louder?
H.
It's an isotope of hydrogen. Right?
H2
It's
isotope.
Right, exactly. But chemically they are exactly the same because they have the same number of electrons, only the number of neutrons are different. Who cares? All of this chemistry is all about electrons. And deuterium and hydrogen and tritium, there are three isotopes. They have exactly the same number of electrons. So chemically they behave exactly the same. No difference at all. So can you guys predict the outcome if those reactions were done? Anybody? Please feel free to walk up and write your answers. Not really. Not for that one. And this is for everybody. It's not just Camilla. So remember which hydrogen goes where. That's why I was pointing it out and I was color coordinating it. The hydrogen from the reagent, sodium borohydride or lithium aluminum hydride, where does that go? The hydrogen from the solvent, where does that go? And then decide the product. Good, no, good. Ooh, that was a good. That was a good.
That was a good.
Yeah, exactly. Again, if you think of the mechanism in your minds, the hydride, which in this case will be D from the reagent, goes to the carbon, and then O minus takes a proton from the solvent. So based on that, you figure out what goes where. Absolutely, yes. Ooh, can't.
I'm not following.
Wait, no, sorry,
One of
this
those is
H.
already there.
Yeah.
Good. Okay, let's write it. Let's write the mechanism to make sense of that. Okay, so just to explain this further, let's start with the first one. So, do you all agree that the carbon is electrophilic,
Yes.
right? Where is the nucleophile coming from? I'm talking about the reaction number 1, 2, 3. How about 1? Where is the nucleophile coming from?
Nucleophile.
It's BD4.
Exactly. Now D and H, they are exactly the same thing chemically. There is no difference between hydrogen and deuterium or tritium. Zero difference. Unless you break open the nuclei, there's no difference. You guys with me? Everybody? So if you follow the mechanism we just wrote a couple of times, what is this going to provide us with?
A deuterium.
A D mine, right? And that's a nucleophile. Attacks the electrophile. Isn't that right? What does that give us?
A alkoxide.
Right, and there was already an H. What's on it now?
D.
Agreed? Everybody?
Yep.
Oh, what did I do? I didn't even notice. Okay, and then what is this doing? It's taking a proton. Who is it taking a proton from?
Methanol.
No. Oh, yes. Sorry. Brain. Methanol. Is there any deuterium in there?
No.
So is it going to give an H or a D?
An H.
So where did the H end up? Exactly. Do you see that? So it's that sequence of events. Make sense, everybody? So without writing the mechanism over again, do you guys agree where would the H go? It'll
There.
go on the carbon. Where would the D go? On the oxygen. Can please make sure you can write the mechanism. So here, This is providing us with the D. Where would that go?
There.
On the carbon, right?
Mhm.
This is also providing us with the D. Where would that go?
Oxygen.
Also the oxygen. So here you've got a dideuterated, whereas here, so strategically, depending on the need, strategically we can place a deuterium in a very specific spot depending on what we need. But does everybody understand that? Yes? Question? Is that okay? Question? Okay. So that's aldehydes and ketones. Did you notice that the number of carbons do not change? The only thing we did was change the functional group. Aldehyde ketone functional group became an alcohol functional group. Let's talk about these two families of compounds. Can someone tell me which family is this?
Ester.
And the bottom?
Halo.
Acid halide.
Acid halide.
Okay, just these two. The others don't really that much, these two. They also react with reducing agents. The only thing with them is though they have to go through two stages of reduction. The first stage, for example, ester, the first stage is it becomes an aldehyde because this gets kicked out. And we'll write a mechanism in detail. That's one stage of reduction, and then what happens to the aldehyde? It becomes a
Alcohol.
what kind? Aldehydes become primary alcohols. Aldehydes become primary alcohols, ketones become secondary. But the thing with esters, as we'll write a mechanism, when they react with sodium, with one of those reducing agents, they first become this, and then that reacts again to become a primary alcohol. So this portion becomes a primary alcohol. And same thing with acid halides as well. In first step, they become an aldehyde. Of course, halide is created as a byproduct. And then the aldehyde becomes a primary alcohol. You guys with me? Yes?
Yep.
So let's look at specific, but before we look at a specific example and mechanism, because they have to go through two stages of reduction, do you think they will need a stronger reducing agent or a weaker reducing agent? Stronger.
Stronger reducing agent.
Sodium borohydride doesn't work because remember, sodium borohydride is a weaker reagent. So if I needed to reduce an ester or an acid halide, there is only one option. Sodium borohydride is not going to work. We have to use lithium aluminum hydride for those because it has to go through two stages of reduction. Everybody okay? Yes? So these guys cannot be reduced with sodium borohydride because it's a weak reducing agent. Aldehydes, ketones, they only have to go through one stage of reduction, so either option is okay. Okay, let's look at an example and see what the product will be and the mechanism and all of that stuff. So let's start with an ester. Okay, that's an ester.
1, 2, 3, 4.
Please notice, what does excess stands for?
Excess.
Excess, meaning?
A lot of it.
A
Why?
lot of it.
Because we need one here and one here. We need at least two equivalents. So let's just use enough because that can be quenched and neutralized by the water. So the point here is one equivalent will not work because we have to go through two stages, which means we need two equivalents of the reagent. Okay, so can someone tell me what will be the product? The product comes from this portion of the ester. It's that portion of the ester which becomes an alcohol. It will always be a primary alcohol from esters. What happens to the other guy? Yes, of course, at least for esters, the other guy becomes an alcohol as well, but we are not chasing that. This is a byproduct. This is not something we are chasing. This is the product we are after.
So it splits?
Yes, exactly. So let's write exactly splits, and we'll write a mechanism there. Let's try and understand why. What's going on? Mechanism. So once again, what can you say about the C double bond O, the carbon?
Resonance.
Okay, what can we say about the carbon of the C double bond O?
It's an electrophile.
So if it's electron poor, that means electrophilic. What can attack it? Sorry.
A hydride.
A nucleophile, in this case, a hydride. Agreed? Yes, exactly the same as what we saw before. Everybody okay?
Mm-hmm.
What does that create? 1, 2, 3, 4. 1, 2, 3, 4. O minus OCH3. And is everybody good? Now, these guys have something that aldehydes and ketones don't have. They have a leaving group. A leaving group which aldehydes and ketones did not have. This falls back, kicks out the leaving group. And you might be thinking, but wait a second, that's a strong base. How is that a good leaving group? Great question. Because the conditions are so highly basic that that's actually a much weaker base than this guy. So it doesn't really matter. So, kicks out the methoxide, and this is where, as you were saying earlier, Carrie, it splits. But when it splits, what does it create? An aldehyde.
An aldehyde.
That's step number 1. That's the first stage of the process. Step number 1. Everybody okay?
Mm-hmm.
But can the aldehyde survive if I have lithium aluminum hydride lying around?
No.
Can the aldehyde survive? No. It can't survive. It will react with lithium aluminum, the reducing agent. And in the same way as we've seen before. And this creates 1, 2, 3, 4. 1, 2, 3, 4. Now, does that have a good leaving group? No. The only things it can kick out is either H's or R's. Those are really, really, really bad leaving groups. We never kick them out. Never. So that's where the reaction stops. Everybody okay?
Mm-hmm.
So what's the purpose of step number 2? This is where the first step stops. So why do we need H2O?
Because it gives it donates a proton.
So then everything that was negative, and also this is lying around too. Of course it's lying around. If you had kicked it out earlier, gets protonated by primary alcohol here, and of course whatever this guy is becomes. But we're not really chasing this guy, we're chasing that guy. But there is a bond that breaks after the first attack by the nucleophile. Do you guys agree? Everybody okay? The mechanism for acid halide is exactly the same. Exactly the same as that. So what I want you to do is write the mechanism, product and mechanism for me. Let's try this. Please go ahead. The product and mechanism. That is exactly the same as this mechanism. So if you want to use it as a guide, please go ahead. Can someone tell me what's the product?
Okay.
Product?
One phenyl methanol.
Two on. How can there be two with meth? Meth means one carbon, right?
One phenyl methanol.
Perfect. So the point is, it's this portion that becomes the alcohol.
Mhm.
So, do you all agree? Right?
Mhm.
Everybody okay?
Mhm.
Let's write a mechanism. What's the first step? Can we do this faster? What's the first step?
Aluminum hydride attacks and adds a proton to the
Not
electrophilic.
proton, Carter?
Oh, adds a hydride
Good. A
to
hydride.
the electrophilic carbon.
Agreed? Yes? What does that create? Creates a minus, O minus. And of course there's a hydrogen. Agreed? What is this going to do? Does it have a leaving group?
Bromine.
Absolutely, we are right there. So what is it going to do? It's going to kick it out. Agreed? What is
Mhm.
that creating? An aldehyde. Br minus is there too, just don't care about it, but agreed, everybody?
Yep.
Can this survive?
No.
No, we have LH lying around everywhere, so this is going to react with another equivalent of aluminum hydride, as we saw earlier, to create a what?
To create alkoxide.
Now it stops. Everybody okay? This is where step 1 ends. So, what happens after that? And what does water do? It gives a proton to the O minus to make the product. Does everybody see that?
Mhm.
Please notice it's exactly the same set of steps. Aldehydes and ketones do it once, they start from here. Esters and acid halides do it twice because they have a leaving group they can kick out. Does everybody see that?
Mhm.
Then can you try that one? Oh. Okay, there we go. By the way, what family of compounds is this?
An ester.
Ester. It's cyclic, but it's an ester.
Cyclic ester.
It's definitely an ester. Mechanism on the board. Please tell me what will be the product. Let's write this quickly. Can I erase this mechanism?
Just 1 second. Thank you.
So looking at what's going on step at a time, finding those shortcuts, can we predict what the product would be for that reaction and a stepwise detailed mechanism? Okay? Anybody? No, it's just the green, because that's so painful to erase for some reason. That brand. The other brand is good. Exactly. 1, 2, 3, 4, 1, 2, 3. Perfect. Yep. Did you all get that? Let's write a mechanism to explain how. Step number 1, what's happening in step number 1?
4.
Sorry. Okay, so the aluminum hydride, please remember it's an ester, so it cannot react with sodium borohydride. It has to react with a stronger reagent. But the aluminum hydride is attacking the electrophilic carbon, agreed?
Yep.
So when that happens, what does it become? O minus with a hydrogen there, agreed?
Yep.
What does this need to do? It has a good leaving group. Where's the leaving group? Right there. Kicks it out. This is where the ring opens up. If it opens up, what does it become? 1, 2, 3, 4. So that becomes O minus, 1, 2, 3, 4. This becomes an aldehyde. Agreed?
1, 1, 2.
Did I count my carbons? 1, 2, 3, 4.
Yep.
Can the what is the aldehyde going to do?
React with water. Or
No, not yet. Exactly. Another equivalent of the aluminum hydride is going to provide another equivalent of hydride to attack the C double bond O,
Okay.
which then becomes O minus. Agreed? This is where step 1 ends. Step 1 finishes there, because there are no leaving groups to be kicked out. This is where step 2 starts, where you then add water, protic solvent, which protonates. Of course, you have lots of it, so gives us the product. But does everybody see that?
1.
Yes? Please practice the mechanisms. It's the same thing over and over again. Questions? So, the 2 questions I have for you. Question number 1. All of these reactions we saw with sodium borohydride or with lithium aluminum hydride, did the number of carbon atoms change?
No.
Agreed?
Yep.
Question number 2, which is the next synthesis reaction. I think it's 4.
Ingredients.
What is the purpose of Grignard? Nucleophilic R. Isn't that right?
Yep.
Now please think about it. I didn't erase this because we want to see the similarity so we can understand. You know, there are these patterns. What is LaH and sodium borohydride giving us? Nucleophilic H. Isn't that right?
Yep.
And where did that nucleophilic H go? It went to the C double bond O. What does RMGX do? Provides us with a nucleophilic
R.
R. Where will that nucleophilic R go?
At the C double bond O.
Exactly the same way as sodium borohydride and lithium aluminum hydride. Exactly the same thing. If I am using a Grignard reagent, let's say R double prime, what is this reagent doing? It's providing us with a nucleophilic organic portion. Isn't that right? So where will the nucleophilic R go? Isn't that right? And what will that become?
An alkoxide.
An alcohol. Exactly the same as sodium borohydride and lithium aluminum hydride. Isn't that right? With one difference. Can someone tell me what is that one difference? You added a what?
You added an R group.
You increase the number of carbon atoms. In that method, all you're doing is converting the functional group from ketone aldehyde ester acid halide into an alcohol. The carbon atoms did not change. Here we added carbon atoms. You guys notice? So, because we added carbon atoms, what kind of an alcohol will an aldehyde become? What kind of an alcohol will an aldehyde become?
A secondary.
A normal aldehyde, secondary, isn't that right? Because we added this. So what kind of an alcohol will ketone become? And please remember, this is important. Grignard cannot come in contact with a protic environment. They have to be separated from each other. That's why it's step 1, step 2, and you will be doing this in lab tomorrow. So if that is the case, the mechanism is exactly the same. That becomes a tertiary alcohol. Everybody okay?
Mm-hmm.
Following this? What about esters and acid halides? Same mechanism, same everything. The only thing is that we are adding R's. So obviously we are increasing the number of carbon atoms. So what about aldehydes and acid halides and esters? So if you have an acid halide or if you have an ester, same thing that you saw with lithium aluminum hydride, it will react with 2 or more equivalents of the Grignard. Same with this as well, 2 or more. To produce, can someone tell me what kind of alcohol will that give us? Are you sure? Tertiary. 2 of them go there. 2 of them go here. Exactly the same mechanism, which we will write in a second, but the 2 of them, that's a tertiary. Now, what's the difference between the tertiary alcohol from a ketone versus a tertiary alcohol from ester or acid halide? What's the difference?
There's more carbons being added.
Say that one more time.
There's more carbons that are being added.
Yes. So therefore, what will be the outcome of that? You're absolutely right. Take that thought forward. Hence, what will be the result of that? The tertiary alcohols you get from esters or acid halides must have 2 of the same things. Must. Ketones, that's not necessary. Because we really added only 1. 2 it came with, we added 1, which can be the same, doesn't have to be the same. But for esters and acid halides, 2 of those have to be the same. But why is this method different from the one we saw? The one we saw earlier does not add carbons, but this one adds carbons. By the way, you're seeing tertiary alcohols on the board, you're seeing secondary alcohol on the board. You're not seeing a primary alcohol on the board. Can I use this chemistry to make a primary alcohol?
No.
Yes.
Oh, like,
Yeah. So let's think about, again, this is called critical thinking. Everything that's on your board, what will be a good starting place to react with a Grignard
methanol.
and convert it into a primary alcohol? Anybody? How many R's does a primary alcohol carbon have?
1.
Where is that coming from?
Grignard.
So what did the original compound have?
2 H's.
H's. Formaldehyde.
Formaldehyde.
It's all about your carbon atoms. Keep track of your carbon atoms. Formaldehyde is the only one aldehyde that can allow this chemistry to provide us with a primary alcohol, because the R comes from the Grignard. Everybody okay?
Mm-hmm.
Now, one thing that I wanted to, let's see some examples and then we'll write mechanisms. Okay. Could you help me pass these out, please? Pass these out, please. Help me pass these out, please.
Give one to me.
Okay. Yeah.
So Grignard chemistry, by the way, this is what you're doing in lab tomorrow. This reaction to make an alcohol out of a ketone is what you're doing in lab tomorrow. Oh, that reminds me. Oh, for the lab tomorrow, you do have to do a little pre-lab calculation, so I don't forget before time runs out. I forget the actual number, but in the lab tomorrow, you are reacting, please take note of this, you're reacting benzophenone. Benzophenone is a ketone with two phenols. We are reacting it with phenyl magnesium bromide. We are not making the Grignard. I will give you the Grignard. You're not making it. And then, of course, after elimination, can you tell me what would the result be? Triphenyl.
Triphenylmethanol.
Triphenyl methanol, absolutely. Of course, we'll write a mechanism for it also, but here's the math you need to do before you come to lab. Are you guys noting this down? I forget how many grams of the benzophenone they ask you to use. So please, can you look this up? Let's say 8 grams, whatever it says, whatever the book says, the procedure says. That many grams of benzophenone. You need to tell me this guy is a 3.0 molar solution in ether. It's a solution, it's not pure. It's the molarity of that solution is 3.0 molar. You got to tell me tomorrow how many milliliters of the Grignard should you use to react with whatever the gram of benzophenone the book is asking you to use. Does that make sense, everybody?
Mm-hmm.
So that's the pre-lab calculation you need to come with tomorrow so that you will tell me, I need this many milliliters of the solution and I will give you that many milliliters of the solution. Sounds okay, everybody?
Mm-hmm.
Please make sure you do the math. Okay, let's look at this handout. The first one, first example. So, butanal, it's an aldehyde, is reacting with a Grignard. By the way, do you remember how to make a Grignard? Does anybody remember how to make the Grignard? Yes, I know, but I didn't mean that. What I meant was, where do we create, how do we get that? From an alkyl halide. What would be the alkyl halide used to create that Grignard? So whatever the R is,
Isopropyl chloride.
that's not isopropyl, that's isobutyl.
Isobutyl
And what are you going to react it with?
Isobutyl chloride.
Magnesium. That's it. So this alkyl halide reacted with magnesium gives us the Grignard. Everybody okay?
Mm-hmm.
Okay, anyway, so what will be the result of this reaction? So where is the R going from the Grignard? Where is the R going?
On the
It's-
electrophilic carbon.
Right? Everybody okay? So the Grignard provides us with an electron-rich R. Agreed?
Mm-hmm.
Please notice it's exactly the same mechanism as sodium borohydride and lithium aluminum hydride. There is no difference in the mechanism. The only thing is, instead of H minus, it's an R minus. That's attacking the electrophilic carbon. Agreed? Is there any leaving group? No, no leaving groups. R's are never leaving groups, H's are never leaving groups. So it stops. This is the end of step 1. Agreed?
Mm-hmm.
What's the purpose of step number 2?
Add water. Add a proton.
So what's the outcome? When that gives a proton, we end up with an alcohol. Do you agree? Make sense?
Mm-hmm.
Let's look at the next one. It's a ketone. Please go ahead.
2,
Make a prediction
4.
of the product. Then we'll write it together.
6.
If it's a ketone, should it make a tertiary alcohol with Grignard or a primary or a secondary? It already has 2 R's, you're going to add another R. Will that give us a primary alcohol, secondary alcohol, or tertiary?
Tertiary.
Tertiary alcohol, exactly. So if we have this, and we are reacting it with, oh, that's not Grignard, but it's exactly like Grignard. It's organosodium, does exactly the same as Grignard. Please do not get confused. Same thing. Looks different, but same thing. Just like Grignard provides us with an electron-rich R, organosodium does exactly the same thing. It provides us with an electron-rich R. No difference. What does that create? Agreed?
Mm-hmm.
And what's the purpose of step number 2? Protonates, gives us a tertiary alcohol. The point is, I hope you're all recognizing that which part already was there in the aldehyde or ketone and which parts came from the Grignard. Everyone okay? Cool. So I think you guys can do the next one. The key is on the let me know if the key is not there. I think it is there, but let me know. But can we go to page 2? Now that's an ester. Page 2, that's an ester. Can I erase this board, everybody? Okay, so how do we, oh sorry, what's going on here? So what do we have? Phenol. And the Grignard is, please notice it says excess. Okay. Does anybody want to take a jab at what the expected product would be? Yes, please, go ahead.
Would they separate?
Yes,
And then,
this part will separate right here, okay? And then?
it'll be go ahead. It'll be,
So this part stays.
and then it'll be an alcohol, so change in alcohol,
And
and then phenol.
2 phenols, because we are providing 2 phenols from here. Mechanism is the same. There it was a primary alcohol because we were using 2 H minuses. Here we are using 2 pH minus, R minuses. Mechanism is exactly the same. So let's write a mechanism for this to understand what's going on, guys. So what's the first step? Electron-rich R attacks the electron-poor C-double-bond-O carbon, right?
Mm-hmm.
Exactly like lithium aluminum hydride. The difference is instead of H minus, it's an R minus. So what does that become? O minus, O and P. Do you agree?
Mm-hmm.
Will this survive? No, because it has a leaving group, which can be kicked out, which will be kicked out. Exactly like sodium borohydride, lithium aluminum hydride. When that kicks out, what does it become here?
A ketone.
A ketone, not an aldehyde this time, because we added an R. There we added an H. So we had an aldehyde. Here we are adding an R, so we get a ketone. Will the ketone survive if there's Grignard around?
No.
Ketone will immediately react with another equivalent of the Grignard and create an alkoxide ion. Does this have a leaving group?
No.
No. So that's where it stops. Can't kick out anything else. So this is where the second step comes in to protonate the O minus. So the final product, please notice 2 of the 3 R's on this tertiary carbon 2 of the 3 R's came from the grain yard. Just like 2 of the 2 H's in lithium aluminum hydride came from the reagent, here 2 of the R's came from the reagent. Do you guys agree? Everybody okay? Okay, can we do one more and then we'll stop and we'll continue, I know, very, very quickly. Can we do the next one? Why don't you tell me what will be the outcome for the next one, and we'll stop there, we'll continue from there Wednesday. I would like to finish this chapter on Wednesday, that's my goal, but we'll see how things go. So this is a cyclic ester which is called a lactone. It is very relevant in biochemistry. There are certain families of compounds such as lactones and lactams, very, very relevant. But as an organic chemist, it's just an ester. There's nothing fancy about it. So what is the reaction?
Ethyl magnesium bromide.
So excess of ethyl magnesium bromide followed by protonation. Any guesses what the product will be?
1, 2,
Sorry?
1, 2, 3, 5.
Uh-huh.
1.
One ethyl, sorry.
Okay. Do you all agree that this bond will break?
Yep.
How many R's will go on that carbon? 2 of them, agreed?
Mm-hmm.
And then what will happen to this O and this O? Will get protonated.
They'll get pronated.
Agreed?
Yep.
So let's write that. 1, 2, 3, 4, 5. So this O becomes an OH. 1, 2, 3, 4, 5. 2, 3, 4, 5. And that is that right? Everybody? Or can I just do just made a mess of that. Doesn't matter. But do you all agree? So please write a mechanism of that. This is one of those reactions whose mechanisms you can't escape because it's one of the most common reactions to see in synthesis using Grignard reagent. So we'll continue from here on Wednesday. For lab tomorrow, please do that math. Tell me how many milliliters of the Grignard solution you will need to react with the given amount of the benzophenone. Molarity is 3.0 molar. Oh, exam 2. I didn't write down the point.
Oh, okay.
So can you bring it tomorrow?
You guys more allow a long one, or? just
It'll take
average?
the whole time, yeah, yeah.
I just wrote out the paper.
Oh, cool. And of course, that
tomorrow,
extra
last
credit exercise due
Yeah, I think
on
so.
when, did we say Wednesday?
Yeah.
Yeah, Wednesday.
I think you said next Wednesday.
You tried.
Good with the
It's worth it.
Oh, I have
We can only control our efforts.